And so I want to start today's class with asking this question. Why isn't the inverse sine of root 2 over 2 equal to 3 pi over 4? It's certainly true. It is true that sine of 3 pi over 4 equals root 2 over 2. So if you break out a calculator and you find the inverse sine, or the arc sine is another name for it. So using a calculator, you'll get that the inverse sine of root 2 over 2 is, if you're in radians, pi over 4. And sine of pi over 4 is also root 2 over 2. So the question is, why is it this one and not that one? Well, it kind of is an involved answer. So let's backtrack just for a minute. Let's talk about a different function completely. Let's look at the graph of y equals x squared. Something you're familiar with. Looks like this. And that's scrap paper if you need it, or blank paper if you need it. Thanks. It's not what we're writing here. So there's the graph of y equals x squared. And if we were going to find the inverse of this function, we would switch x and y. That's the first step to finding the inverse. Now, I'm going to stop there for just a second. If we switch x and y, we get x equal to y squared. Let's graph that. So I graph x equal to y squared. What does it look like? Yeah, exactly. It's a parabola, but it opens to the right. And you get the full parabola, right? You get the top part and the bottom part. So I'm graphing x equal to y squared. It looks like this. Now, can anyone tell me why this might be a problem? It's not a function. Exactly. That's not a function. So when we find an inverse function, we have to do something. So what we do here is, if we're actually trying to find the inverse function of y equal to x squared, we say, well, y equals x squared is technically not invertible. It's a function that isn't one-to-one, also known as failing the horizontal line test. So if you draw a horizontal line, let me grab my other pens here, sorry. Apologies. So this function y equals x squared fails the horizontal line test. When I draw a horizontal line, it goes through more than one place. And when you interchange x and y, that corresponds to the interchange failing the vertical line test, which means it's not a function. So what do? We restrict the domain of the original function so that it is one-to-one. So if I want to invert this, what we're going to do is we're actually going to take y equals x squared and restrict the domain to x greater than or equal to 0. So if we look at that here, now y equals x squared is going to look just like the right half, where x is greater than or equal to 0. And now if we interchange x and y, we get x equal to y squared. Welcome, that's extra paper if you need it to take notes on. So if we interchange x and y, now I've interchanged x and y. I said before that x had to be greater than or equal to 0, but now I'm changing their roles. So now what that means is x greater than or equal to 0 means that y is going to have to be greater than or equal to 0, because we've interchanged who's who. And so when I solve for y now, I get y equal to, well, if I was taking the square root of both sides, I'd really have a plus or minus the square root of x. But we just said y has to be positive because we're restricting x to be positive. So we're limited to that part there. So when we draw the inverse, it looks like just that. So to catch up people who came in a little bit late, we started by asking the question. We'll come back to this, don't worry if you can get to slow down. We start by asking the question, why isn't the inverse sine of √2/2 equal to 3π/4? And so I want to point out that sine of 3π/4 is √2/2, but the inverse sine of √2/2 is π/4. And we also know for sure that, and of course, sine of π/4 is √2/2. And so we're asking the question, well, why do you get one value instead of the other? And it's the same kind of reason when you take the square root of 9, you get 3 and not -3. Because we've kind of decided as a mathematical community that some functions have certain domains and ranges. And specifically, we were looking at, when you look at y equals x squared, that function is not invertible. When you flip it over like that, when you interchange x and y, you get something that's not a function. And so the way we deal with that, which we're about to do for the sine function, is we restrict the domain of the original function so that we don't have all this stuff over here. Oh, sorry, thank you. And so that we don't have all this stuff down here. It's making it not a function. So when you're trying to find the inverse of y equals x squared, you get y equal to the square root of x. And we just recognize that, oh yeah, we're not thinking about this other part down here. We're going to do the same thing for sine. So let me show you what I mean. So let's graph sine of x. Not too detailed. There's my period of 2π, cut it into 4 spots, and maybe a couple spots to the left here. So sine starts at 0 and then goes up to 1, back to 0, down to -1, back to 0, and to the left, kind of looks like that. So here's my sine function. And it continues on. Great. So I think you all can tell if I switch x and y, I'm definitely going to fail the vertical line test. Hardcore. But let's graph it anyway. So if I graph x equal to sine of y, I'm really just changing my axes. So I would actually like turn my paper this way to do it. Really, I think that's going to be so. So instead of having the pi values on the x-axis, I'm going to have the pi values on the y-axis. So I'm going to have pi/2, pi, 3π/2, 2π, and -π/2, -pi, -3π/2, -2π. And so if y is 0, x's sine of 0 is 0. If y is pi/2, sine of pi/2 is 1. Sine of pi is 0. Sine of 3π/2 is -1. Sine of 2π is 0. So it looks like this. It's hard to draw it this way. That's why it doesn't look as good. But I think you can all see, definitely fails the vertical line test, without a doubt. So what do? We want there to be an inverse sine function. It's a useful function to have. So what we do is we take our sine function and we restrict the domain. And the domain we're going to restrict it to, so that it's still 1-to-1, is the domain from this point here to that point there. So this section right here, from -π/2 to π/2, is where you're going to restrict sine so that when you invert it, you get something that is a function. So restricting the domain of sine from -π/2 to π/2 means we're going to be restricting the range of x equal to sine of x from -π/2 to π/2. So this is the graph of x equal to sine of y. And here's the more important graph of y equal to inverse sine of x. which is just this red part right here. And it goes from this point over here at -1, negative pi over 2 to this point over here at 1, pi over 2. It's not a very big graph. There's very much not a lot to it. But that is your graph of the inverse sine function. And importantly, we don't so much care about the graph. What we do care about is the following. The function inverse sine of x has a range of negative pi over 2 to pi over 2. Meaning, when someone asks you what's the inverse sine of some angle, the only values you can give them are between negative pi over 2 radians and pi over 2 radians. Or if you're talking degrees, negative 90 degrees or positive 90 degrees. So for example, the inverse sine of √2 over 2. When I read this, those aren't the words I say in my head. When I look at this, here's what I think you should say. This is the angle whose sine is equal to the value, √2 over 2. I know it's a lot of words to say instead of inverse sine of √2 over 2. But it makes sense. Inverse functions undo what the other functions do. So sine of a pi over 4 equals √2 over 2, and the inverse sine function undoes that. Inverse sine of √2 over 2 gives you back the angle you started with. So the inverse sine of √2 over 2 is pi over 4. And no other possible angle. There isn't a different answer to this question because it's a function. And functions give you one output for every one input. We could also ask, what's inverse sine of negative √2 over 2? The nice thing about inverse sine is if you know the inverse sine of a positive value, the corresponding negative value has the corresponding negative angle. So the inverse sine of negative √2 over 2 is negative pi over 4. Because sine of negative pi over 4 is negative √2 over 2. Yes, there are other answers, right? Sine of 5 pi over 4 is also negative √2 over 2. Sine of 7 pi over 4 is also negative √2 over 2. But we are all deciding together, or someone has decided for us, and we are going to go along with it, that these are the values we're picking for the inverse sine function. Let me pause for questions. Yeah, Malik. Well, so the restriction on the domain became the restriction on the range. But yeah, yeah. So the inverse sine function gives you angles that are in quadrant 4 or quadrant 1. But specifically, you're going backwards to quadrant 4 and forwards through quadrant 1. So you're going back. In fact, we can even write it this way. I want to see what I'm writing. The range, I'm going to write again, of y equal to the inverse sine of x is, I just saw the comment, negative pi over 2 to pi over 2, which if you're thinking about the unit circle, means we're going from 0, we're going this way to theta equal to pi over 2, and back this way to theta equal to negative pi over 2. That's the range of the inverse sine function. Yeah.
So like in a different function, like the amplitude or like the shift, everything is different. Like the range would still be pi over 2.
Yeah, and so we don't typically talk about the inverse sine function with having different range or amplitude. Like we don't do all the shifting stuff that we do with sine to inverse sine.
Okay.
We're really mostly like, I drew the graph for you guys so you all could see it. It's not something we often graph really. And no one's ever going to ask you to graph like 2 inverse sine of x or anything like that. The reason we mostly talk about it is because we want a way of finding the answer to a question. Like if I'm trying to solve sine of x equal to 0.63, I have no way of doing that without a calculator. And the solution is going to be x equal to the inverse sine of 0.63. And that angle between negative pi over 2 and pi over 2. I'd actually have to use a calculator though to figure out what that answer is. So the point here isn't that it's something we like to graph, it's that it's a tool we use to kind of figure out what things are. I do want to differentiate. Finding, let's say, the inverse sine of negative 1/2. So again, what does that say? It says I'm looking for the angle where sine is equal to negative 1/2. So what angle is that? Is it pi over 6 or pi over 3? I should say, what reference angle is that? Is it pi over 6 or is it pi over 3? Pi over 6. But I know it's actually not pi over 6 because I want inverse sine of negative 1/2. So the answer should be negative pi over 6. Because if you look back, right? If you go negative pi over 6, you're down there. And the point there is exactly root 3 over 2 comma negative 1/2. And the sine value is negative 1/2. So that's how you find the inverse sine of negative 1/2. Versus if I said a different question, which feels the same, if I said to solve sine of theta equal to negative 1/2, where theta is between 0 and 2 pi, then we're still going to use that information. Right? We know that sine of pi over 6 is equal to 1/2. But now our answers need to be in which quadrants? Where sine is negative. Well, first of all, there's going to be multiple answers. Right? You're getting an answer in quadrant 3 and in quadrant 4. So our reference angle here is still pi over 6. And our quadrants are quadrant 3 and quadrant 4. In quadrant 3, our angle is going to be pi plus pi over 6, which is 7 pi over 6. And in quadrant 4, our angle isn't going to be negative pi over 4. It's going to be, sorry, negative pi over 6, apologies. It's going to be positive 11 pi over 6. It's a coterminal angle, but it feels a little bit different. This isn't a huge deal, but it is something I want you to be aware of. Yeah.
You said that we'll see this in calculus. Like, in what way?
Minimally.
Okay.
It does that. I mean, to be like, and it really does. It depends on which calculus class you take. You would see it more in the 21 series. You would see it less in the 16 series, and probably even less in the 17 series. In each of those series, at some point they do talk about the derivatives of inverse trigonometric functions. In the 17 series, I believe they only talk about the derivative of the inverse tangent, whereas in the 16 series, they definitely talk about the derivatives of all the inverse trig functions typically. So that's one of the reasons you're seeing this, is because it does come up later. Let's talk about two more of them, inverse cosine and inverse tangent. So inverse cosine has the same sort of deal, right? It's got the same shape as sine, it's just shifted a little bit, and we need to make the same sort of restriction. So here's our cosine graph. Starts at 1. And then it goes to 0. And then it goes to -1, and then back to 0, and then back to 2 pi. If we went to the left, we went pi over to the left, we end up there. It'll look like this. Great. And so I'm not going to draw x equal to cosine y because you all can see that it's not going to be a function. But the question here is, what domain do I need to restrict this function to so that it is 1-to-1? And here's an answer that's not right. It's not going to be the same as the sine function, right? If we pick from negative pi over 2 to pi over 2, it's not going to be 1-to-1, right? It fails the horizontal line test. So in this case, we're going to pick something else. What's one choice that would work? Pi to 2 pi would definitely work. It's not what everyone's picked. But it would work. You're totally right. Pi to 2 pi is a totally legit answer that somebody else could have decided way back when they made this choice, and we'd all be using that instead. Typically, if we can choose it, we like to choose the first quadrant. So I definitely want from 0 to pi over 2, and then what else would be good to pick along with that? Pi over 2 to pi. So the choice we're going to make, the choice that's been made for us, is that we're going to restrict this domain to be from 0 to pi.
The other one does.
The other one totally would work, but that's not the one we've all used. So when we define, what's that?
That's the default.
Yeah, so the way that all textbooks define the inverse cosine function is for f of x equal to the inverse cosine of x, the range 0 to pi. Right, we're going to restrict the domain of cosine that, but then when we graph the inverse function, right, we're taking this thing here, this piece in, I'm going to try and make it so you can see the red. We're going to take that piece in red from 0 to pi, and we're going to interchange the x and y values. Right? That's how we graph the inverse. So that's an easy way of graphing the inverse. So instead of getting the point 0, 1, I'm going to get the point 1, 0. Instead of getting the point pi over 2, 0, I'm going to get 0, pi over 2. Instead of getting the point pi, -1, I'm getting -1, pi. And here is what my inverse cosine graph looks like. Right? It's missing all the rest of it that we keep doing all this. And so you can see, oh yeah, that graph has a range from 0 to pi. So if somebody asked you, what's the inverse cosine of √2/2? Positive values are always nice. Positive values, you just get the answer that's in the first quadrant. So inverse cosine of positive √2/2 is going to be pi over 4. Inverse cosine of negative √2/2. All right. What's an angle between 0 and pi where cosine is equal to negative √2/2? I know the reference angle. It's pi over 4. What's the actual angle? 3 pi over 4, right? It's got to be the one that's in quadrant 2, because that's the only other quadrant we have to choose from. In a similar way, we could say inverse cosine of √3/2 is pi over 6. Again, when I'm reading that, I'm really saying the words in my head. What angle do I take cosine of and get √3/2? Oh, the angle is pi over 6. Whenever you see inverse cosine of something or inverse sine of something or inverse trig function of some value, you should always be thinking that your answer is an angle. You're always looking for the angle. That if you took cosine of that angle, you would get √3/2. Or if I wanted inverse cosine of negative √3/2, the answer would be 5 pi over 6. Somebody asked, this is off topic, but do we have any more information about the placement test? Because I haven't gotten an email yet. I do not have any more information yet. If you're concerned, so the placement testing period starts the 8th, I believe, which is a week from today. It's like the 8th to the 14th. Sometimes people are just not on top of their stuff, right? So it should be coming from the math department. If you're concerned, you might send someone in the math department an email and be like, hey, I haven't heard anything yet. You also can manually register, although you shouldn't have to if you're registered for a class next quarter. So I don't have any more information at the time. I let my boss know that my students hadn't heard anything from that department, not that she, like, we're not the math department, right? So they certainly should be letting you know, but I'm not in charge of what they're doing.
What if you wait this?
That's a good question. I don't know the answer to that question. I would err on the side of caution and manually register. All right. So back to this. Questions about this before we talk about inverse tangent, which is going to be the same sort of deal. Inverse tangent is kind of neat. Inverse tangent is definitely the one that you are taking the 17 series that you will see for sure. The other two, not so much. So we're going to do the same sort of thing. Let's graph tangent. I know we graphed it before. So I'll remind everybody that tangent has vertical asymptotes at pi/2 and then every pi later. So because the period's pi. So we're going to have a vertical asymptote at pi/2. And then if we add pi to that, we're going to get a vertical asymptote at 3pi/2. And if we subtract pi, we're going to get a vertical asymptote at -pi/2. If we subtract another pi, then we're going to. And here's what tangent looks like. And it just keeps going. Same deal here. Every trig function fails the horizontal line test, right? Every trig function is periodic, meaning at some point it's going to have the same y values. It repeats itself every pi. So what's the period I should pick, or sorry, not the period, what's the domain I should pick for tangent for it is 1-to-1? Well, the nice thing here is that it's virtually the same as the choice for sine. We're going to pick from -pi/2 to pi/2, except we can't include the ends because it's not defined there. So we're going to restrict the domain from -pi/2 to pi/2. So we're going to get this nice piece right here in the middle. So that's the tangent function, and we're going to invert that. So when you invert something that has asymptotes, those asymptotes also invert. Meaning instead of x equal to pi/2 as a vertical asymptote, we're going to get y equal to pi/2 as a horizontal asymptote. And we're also going to get y equal to -pi/2 as a horizontal asymptote. And we see it here. So the way I would think about this is as the x values get closer to pi/2, the y values get very, very large. Well, that's going to switch. So now as the x values get very, very large, the y values get closer to pi/2. It'll look like this. I mean, it literally just looks like we took the tangent function and flipped it across the line y equals x. So there's your inverse tangent. It's kind of neat. One thing that's worth knowing about inverse tangent that does come up in calculus is that for y equal to the inverse tangent of x, as x gets very large, I'm avoiding using the word limit there, but you could say the limit as x goes to infinity. But as x gets very large, the inverse tangent of x gets close to the value of pi/2. That does come up, although people use the more language of limits there, where they say the limit as x goes to infinity of the inverse tangent of x is pi/2. So it's getting closer and closer and closer to pi/2 as x is larger and larger and larger. And then we can ask the same sorts of questions, like what is the inverse tangent of some known values, like the inverse tangent of -1. Okay, so I want you to say this in your head. I'm trying to find the angle whose tangent is equal to -1. Actually say it. You can even say it out loud if you really want to. All right. What's our angle? What is our angle?
Pi over 4.
It's something with pi over 4. Is it pi over 4? No, because tangent of pi over 4 is positive 1. So what's the angle we actually need? Is that worth that? So you're not wrong, but we've already made the choice. We've already made the choice that the range of the inverse tangent function is from negative pi over 2 to positive pi over 2. So the only valid choice when you're trying to find the inverse tangent of negative 1 is negative pi over 4. So this is the nice thing about inverse sine and inverse tangent. If you know what inverse sine of the positive value is, or inverse tangent of the positive value is, you automatically get the negative one just by throwing on a negative. So if I was trying to find the inverse tangent of the square of the negative square root of 3, I would first say, well, what's inverse tangent of positive root 3? It's the angle. If I take tangent of it, I get root 3. That's going to be pi over, it's either 3 or 6. It's 3. And after I know that, I automatically, oh, well, that's going to be negative pi over 3. So if you know inverse tangent of a positive value, it's very easy to get the inverse tangent of the corresponding negative value. In a similar way, if you know that the inverse tangent of root 3 over 3 is pi over 6, then the inverse tangent of negative root 3 over 3 is negative pi over 6. And again, what this really is saying to us is this is saying, oh, that's because tangent of negative pi over 6 is equal to negative root 3 over 3. Right, that's the relationship between the function and its inverse function. One function has a certain input and a certain output. The other function reverses those roles. For tangent, the input's negative pi over 6, the output's negative root 3 over 3. For inverse tangent, the input is negative root 3 over 3, and the output is negative pi over 6. It's the whole deal, right? That's what inverse functions do. They switch the role of x and y. That's all the, so I will say that's not all there is to say about inverse functions, inverse trig functions, but inverse cotangent is fine, it's just like inverse tangent. Inverse secant and inverse cosecant are weird. They're actually weird because, so now I said, like in these previous ones, we're going to pick a domain to restrict it to. For inverse secant and inverse cosecant, there is disagreement in the mathematical world about which domain we should pick. Sometimes we pick a certain domain, like for inverse secant, sometimes it makes sense to pick from 0 to pi. Sometimes it makes sense to pick from 0 to pi over 2 and from pi to 3 pi over 2. There are reasons for this that I don't want to get into because, I mean, the reasons are really one way it looks nicer when you graph it, and the other way is nicer when you take the derivative. That's the real truth. One choice, the graph makes way more sense and also corresponds to cosine. The other way, the graph looks janky, but the derivative doesn't have an absolute value in it. And you really don't want to have an absolute value in your derivative. So I wouldn't worry too much about inverse secant and inverse cosecant. They probably won't get talked about very much in either 16 or 17. If you're taking the 21 series, then you should worry about it. But yeah. The other thing I wanted to say, speaking of secant and cosecant, is I wanted to graph them for you. Not inverse secant, inverse cosecant, but just secant and cosecant. So there are three trig graphs I haven't shown you because I feel like I owe you. First, the graph of y equal to cotangent of x. Before I secant and cosecant. Cotangent looks, so this is true of all cofunctions. Sine and cosine look very similar, right? They're graphs, they're like the same, they're just shifted from each other. Tangent and cotangent are also going to look very similar. Secant and cosecant are also going to look very similar. Graphing cotangent, I would remember that it's cosine x over sine of x. And so I'm actually going to think about where is this undefined? Right? I could start plugging in values. They always tell me like, well, I'm gonna plug in values now. If I look at my usual like 0, pi over 4, pi over 2, 3 pi over 4, and pi, because unlike sine and cosine, tangent and cotangent have a period of just 1 pi, not 2 pi. Cotangent of 0 is going to be, let's see, cosine of 0 over sine of 0. That's going to be 1 over 0, which is undefined. Meaning we're going to have a vertical asymptote at 0. And cotangent of pi over 4 is going to be 1 because it's cosine of pi over 4 over sine of pi over 4, which is root 2 over 2 over root 2 over 2. And cotangent of pi over 2 is going to be cosine of pi over 2 over sine of pi over 2, which is going to be 0 over 1, which is 0. And then in quadrant 2, we get the same values, just negative. Cotangent of pi over 3 pi over 4 is going to be negative 1. And cotangent of pi is going to be undefined as well. So let's look at the graph of this. 2 pi, vertical asymptote of pi, and 0, which I'm not going to draw because there's an axis there. And then we know that cotangent of pi over 4 is positive 1 there. And cotangent of 3 pi over 4 is going to be negative 1. This one's actually going to go down from left to right. And then it repeats. Yeah, same kind of deal down here. So there's one period plus a little more of cotangent. Something else I might mention just because I'm noticing it. Cotangent is an odd function. I know it kind of looks funky, but if you rotated it 180 degrees around the origin, it would look the same. Tangent, also an odd function. Rotated 180 degrees looks the same. Sine, also an odd function. Rotated 180 degrees looks the same. Cosine, not an odd function. Cosine's even. It has a symmetry about the y-axis. All right, last two graphs. Again, none of this stuff is going to be on your midterm or just your final, but I felt like I should show it to you. So if this isn't sinking in, that's okay. But you should be aware some of this might come up next quarter when you take calculus. So I didn't want to leave you in the lurch. All right, let's look at cosecant and secant real quick. So if I ever have to graph secant of x, I remind myself that it's 1 over cosine. And what I really do is I actually think about what cosine is going to do first. So here's my method that I think works great for graphing cosecant. Graph cosine. Sorry, graphing secant. Graph cosine. So let's go 2 pi. Let's go 2 pi in this direction. And you notice when I do this, right? I mark out my 2 pi and then I cut it into 4 quadrants. And I cut it in half and then each of those in half again. And then do the same kind of thing on the left. Well, actually, no, I'm just marking it out really. Doesn't have to be perfect, it should look decent. And okay, so I know that cosine starts at 1, and then the next value goes to 0, and then to negative 1, and then back to 0, and then back to 1. And the same thing on the left. So we're going to graph cosine. I'm not going to really graph, I'm going to graph kind of dashed here. It would look like this. All right, so if we know that if we know some values of cosine, we can find the values of secant. So if x is 0, cosine of 0 is 1, and secant of 0 is also 1. So I get 1 right here. Now, pi over 2 might not feel super helpful. If we plug in pi over 2, cosine of pi over 2 is 0, And secant is going to be 1 over 0, which is undefined. Meaning, what kind of feature are we going to have at pi over 2? Yeah, a vertical asymptote. Okay, but that doesn't help me so much because I'm not exactly sure what happens between there and there. So here's what I want to point out. Let's look at one more value. Let's say cosine of pi over 3. Cosine of pi over 3 is 1/2, which is probably right about, I don't know, here on the graph. Well, the reciprocal of 1/2 is what? Right, so secant is going to be 2 at the same angle value. Here's the way I typically think about this. As the cosine values get closer and closer to 0, the secant values get larger and larger and larger because you're dividing by a smaller and smaller number. So as cosine moves towards the x-axis, secant moves away from it. And then you can do the same thing down here. If cosine of pi is equal to -1, then secant is 1 over -1, which is also -1. So they actually touch at those points. The cosine graph and the secant graph touch here, and here, and here, and here. But as cosine moves towards 0, secant moves away from it. And it just keeps doing this. And same thing to the left. There's a vertical asymptote here, looks like that. I should mention these are not parabolas. They do kind of look parabolish, but they're not parabolas. Our parabolas can keep going wider and wider and wider, and these definitely have a very stringent limit on how wide they get. But they do kind of have a parabola-esque shape. So there's secant. Kind of gross. Now, the nice thing about cosecant is it's going to be virtually the same. If you know what secant looks like, you know what cosecant looks like. You're just going to shift it over pi over 2, I think, to the right. The way I would graph cosecant is still by graphing its reciprocal sine and then drawing it kind of. I kind of think about it. What I'm doing is I'm taking the cosine function here and I'm kind of flipping it away from the x-axis. I'm taking this part here that's going down and then flipping it kind of up. This part here that's kind of looking like this and then flipping it over that way. It's kind of a weird way of thinking about it, but it's worked for me for many years. So let me show you the last one, and then that's all I got. So we're going to graph cosecant of x, which is 1 over sine of x. And let me show you kind of the fastest way I can do it. So I'm going to plot my usual kind of 5 sine points. So I know that sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 2 is -1, and then back to 0. Okay, I'm not even going to draw the sine graph this time, like I did the cosine graph. I'm going to say, well, if sine is 0, cosecant is going to have a vertical asymptote. I'm going to have vertical asymptotes at x equal to 2 pi, x equal to pi, x equal to 0. Really, x equal to every multiple of pi would be a vertical asymptote here, right? If you kept going. And then here, instead of going down like that, we're going to go up, up, and away like that. And here, instead of going closer to the x-axis, we're going to go away from the x-axis. Secant and cosecant are always going away from the x-axis. They never actually touch the x-axis. They're always far away from it. They have a strange range. All right. Okay. So there is one period of cosecant. You could draw more. It just keeps doing the same thing, right? So we keep going like that. Here would be like that. But I don't think you need to draw any more than one period.